Good morning, students. In the last session, we studied about atmospheric refraction and twinkling of stars. Why do the stars twinkle but planets do not twinkle? We have discussed the effect of atmospheric refraction. Now, one more interesting phenomenon about the atmospheric refraction is advanced sunrise and delayed sunset. The sunrise that we see early in the morning actually is advanced by 2 minutes. We are seeing the sun which is still below the horizon. We are seeing the actual sun still actually below the horizon. So sunrise occurs 2 minutes early. In the same way, during sunset, the sunset is in the west direction. During sunset, we see the sun which has already set down below the horizon. 2 minutes delayed. Means the sun already had set down, but still we will be able to see the sun above the horizon. So the sunset gets delayed by 2 minutes and the sunrise gets advanced by 2 minutes. Sunrise gets advanced by 2 minutes and sunset gets delayed by 2 minutes. So total delay in the whole daytime, total delay in the whole time becomes 2 plus 2, 4 minutes delay in the whole day. So how is this? It is again due to atmospheric refraction. Due to atmospheric refraction. How does it take place? Look at the diagram. This is the diagram of Earth and this is the atmospheric layer around the Earth. This is the thick atmospheric layer around the Earth. And here is the observer. Now suppose the sun is below the horizon. The sun is now below the horizon and is going to have sunrise. When the sun is below the horizon, this is the horizon, below the horizon, the sun rays, look at this. The sun rays after entering into the atmosphere, they bend towards the normal because the sun rays are entering from vacuum into the atmosphere. The atmospheric layers are having little density, so their optical density will be higher than the vacuum. Therefore, the rays of light bend towards the normal. Due to bending of the rays of the light towards the normal, when the observer observes them, here is the bending of ray of light. When the observer sees them, that these rays appear to have come from this point. The rays which are reaching here appear to have come from this point. So the sun will be seen above the horizon. So this takes place 2 minutes early. So sunrise takes place 2 minutes early. In the same way, we can assume that this is sunset. What happens during sunset? The sun goes down the horizon. When the sun goes down the horizon, now suppose it has already gone down the horizon, the rays of sun are still seen here. The rays of sun below the horizon, after entering into the atmospheric layers, they undergo refraction, bend towards the normal, and these bent rays are observed as if they are coming from this point. So still the sun is seen above the horizon. So this process of complete sunset takes place 2 minutes more. So there is a delayed sunset and advanced sunrise due to atmospheric refraction. This is very interesting. Now next we'll learn some interesting natural phenomena that we see around us. Like the sky appears blue. just during sunrise or during sunset, the sun appears reddish, beautiful reddish in color, and around the sun, the sky appears reddish during sunrise and during sunset. Then flattening of even the same thing, atmospheric refraction. See here, I forgot to tell you one more thing. During the sunset, you must have observed the perfect circular disk of the sun will be appearing to be little bit flattened. When the sun is getting down here, this is perfect circular disk of the sun. As and when it approaches the horizon, the shape of the sun becomes little flattened. The reason for the flattening of the sun just before the sunset is also the atmospheric refraction. Actually, this is the perfect spherical or perfect circular shape. The bottom part of this sun will be seen at the top. How is it again? The bottom part of the sun still sending the rays of light. These rays of light, after entering into the atmosphere, they again undergo refraction. Still the bottom part of the sun is seen just above the horizon because of bending of rays of light due to atmospheric refraction. So flattening, shape of sun, just before sunset is also due to atmospheric refraction, that is bending of the rays towards the normal. So the bottom part of the sun still appears to be on the above part of the horizon. So instead of the sun appearing to be circular, it appears to be oblong, it appears to be flattened at the bottom. So this is due to atmospheric refraction. Now let us learn about very interesting phenomena such as blue color of the sky, color of water in deep sea, the reddening of sun at sunrise and sunset. What are the reasons for these wonderful phenomena? The reason for these wonderful phenomena, we are going to learn it as important thing, that is scattering of light. Let us learn scattering of light. The interplay of light around the object around us gives rise to spectacular phenomena in our nature. The blue color of sky, and water of ocean, deep water of ocean, blue color of sky, deep water with a lot of depth of ocean. And when you see the far away mountains, the far away things appear blue. So the blue color of the sky, water of ocean, reddening of sun, and sky around it, red color of sun and sky around it, just before sunrise or just before sunset, and just after sunrise. The sun appears to be beautiful red sphere, red disk just before sunset and just after sunrise, and blue color of the sky. These are all beautiful phenomena that we see in our nature. What is the reason for this? The reason for this is scattering of light. You see, when the light enters into our atmosphere, the atmosphere consists of several fine particles like air molecules. You know air molecules. Air consists of nitrogen, oxygen, carbon dioxide and other rare gases, along with dust particles, water molecules in the water vapor, and then smoke particles. So the atmosphere consists of fine particles such as dust particles, water molecules, tiny water droplets, and smoke particles, air molecules and so on. These molecules are of different sizes. So when the sun rays enter into such layer of atmosphere, the sun rays are scattered by these molecules. You have studied Tindal Effect in last year in chemistry. When the light enters into a clear solution, when the light enters into a pure clear solution, the light beam will not be seen. The beam of light will not be seen. But when the light enters into a colloidal solution is the solution having larger particles, larger molecules. When the light enters into the colloidal solution, we can see the beam of light through that colloidal solution. This effect is called as Tindal Effect. Similar thing take place even in the atmosphere. How do we see light? How do we see the sky? How do we see the cloud? The cloud, generally the clouds appear white. How do we see white color of the clouds? So answer for all these is the very important phenomenon called as scattering of light. The light gets scattered. Scattering means getting reflected in all possible directions. When the light gets scattered by these particles, that light enters into our eyes and then we will be able to see the light around us. When it falls on the objects, it gets reflected and enter into our classroom. This is what we call as diffused sunlight. The light gets reflected and diffused in all possible directions. So this diffused light enables our eyes to see the things around us. So that is due to scattering of light. The scattering of light takes place by different amount, by different sized particles. Very fine particles are also there, bigger particles are also there. For example, carbon dioxide, nitrogen, oxygen molecules are very fine, very small, can't be seen with our eyes. The molecular size of nitrogen, carbon dioxide and oxygen is much smaller than the wavelength of light. When the light enters into such a layer of atmosphere consisting of air molecules, the light gets scattered in such a way that the shorter wavelengths of the light get scattered away. The shorter wavelengths of the lights are towards the blue, indigo, violet. If you recall, white, VO with GR. As you move from violet, indigo, blue, green, yellow, orange, red, wavelength increases. Wavelength of light increases as you move from violet to red. Indigo is having more wavelength than violet. Blue is having more wavelength than indigo. Green is having more wavelength than blue. So red is having highest wavelength. Violet is having least wavelength. But violet and indigo are not prominent colors for our vision. They are not visible prominently to our eyes. So the only next visible light is blue. So these air molecules like oxygen, carbon dioxide and nitrogen being very small particles, small size, whose size is shorter than wavelength of light. The size of these air molecules, nitrogen, oxygen, carbon dioxide, are shorter and smaller than wavelength of light. These molecules scatter the light of shorter wavelengths to a greatest extent, to a greater extent. So the angle of scattering by these molecules, if it is angle of scattering, let us say it is called as theta. This angle of scattering is found to be directly proportional to fourth power of wavelength. I think you got the point. Lambda raised to 4. It is inversely proportional to fourth power of wavelength. It means shorter the wavelength, greater is the angle of scattering. Where theta we can call it as scattering angle or angle of scattering. So for such molecules whose size are very small compared to wavelength of light, the angle of scattering is inversely proportional to fourth power of wavelength. So shorter the wavelength, greater is the angle of scattering. Therefore, violet and indigo are scattered to the maximum extent with maximum angle of scattering, but violet and indigo are not prominent to our eyes. So blue being shorter wavelengths, blue light is scattered most. Blue light is scattered most away from the atmosphere. Therefore, whenever you see the faraway things appear blue. The faraway mountain appears beautiful blue in color. Durada gudda kandige nunnage. The faraway mountain appears bluish, very beautiful. The faraway sky appears bluish in color. The reason is blue colored light is scattered with maximum angle because the wavelength of blue color is minimum. It should be violet, but violet and indigo are not prominent to our vision, to our eyes. Therefore, violet sky is appearing to be blue. Therefore, sky appears blue. This is the reason the sky appears blue. Then what happens? Just during sunrise or just during sunset, the sun appears to be red in color. The sun appears to be reddish in color, and the sky around sun also appearing to be reddish orange in color. The reason is during sunset or sunrise, the sun rays are passing through maximum thickness of our atmosphere. The sun rays are passing through maximum thickness of our atmosphere. So the blue, green, yellow and violet, indigo, blue, these colors are scattered away. They are scattered away from the sun. So if you look at the sky which is away from the sun, that sky appears to be blue. But the red color is least scattered. The red color is least scattered because wavelength of red is maximum. See here. If you just write the wavelength of violet is about 4000 angstrom, and wavelength of red, this is lambda is notation for wavelength. Wavelength of red is around 7500. So if you consider the wavelength of red with that of violet, it is nearly 1.8 times. 1.8 times the wavelength of violet. You can look at this. It is more than 1.8 times. The wavelength of red is more than 1.8 times the wavelength of violet. Therefore, the air molecules do not scatter red light at all. So, thickest air molecules during the sunrise or during the sunset will scatter the red color to the least, with least angle. Therefore, around the sun and the sun appears to be reddish just after sunrise or just before sunset. But what happens during daytime? During daytime, the sun, say for example at noon, the sun is over our head. When the sun is over our head, the sun rays are passing through smallest thickness of the atmosphere. The sun rays are entering through smallest thickness of the atmosphere. As a result, if you look at a faraway sky, the faraway sky appears to be bluish. But around the sun, you will find white, almost bright sunshine. You will not be able to see the sun at all. Almost all the colors are equally scattered during daytime. The reason is scattering of light depends on the angle of scattering depends on inversely on fourth power of wavelength. It is inversely proportional to fourth power of wavelength. This is how we can give the reason for reddening of the sun and the sky around it just before the sunset and just after the sunrise. Generally, the clouds appear white. This is another one. Clouds, when you observe during daytime, the clouds appear white. The clouds consist of tiny water droplets. These tiny water droplets are larger in size compared to that of these air molecules, like dust particles or these air molecules like oxygen, carbon dioxide and nitrogen. Compared to the size of these molecules, the tiny water droplets are large in size. Then this condition doesn't hold good. This condition is not valid. These tiny droplets of water in the cloud scatter the light equally in all the directions. When the light is scattered equally with equal angles in all the directions, so all the colors are equally scattered with same angle. Therefore, the clouds appear white. So scattering of light takes place equally in all the directions. Therefore, the clouds generally appear white in color. So I think we got the reason why the sky appears blue. The sky appears blue because of the fact that the air molecules being very small in size, the scattering of light is inversely proportional to fourth power of wavelength. Means those shorter wavelengths are scattered with the maximum angle of scattering compared to those longer wavelengths, orange and red, or longer wavelengths. These longer wavelengths are scattered least. Therefore, the sky appears blue. One more thing you must have observed, the danger signal. The danger signal is always red. Why the danger signal is always red? Even for the vehicles, the headlights behind the vehicles, they are red. Even if the vehicle is far away, we can see the vehicle. The red danger signal is due to the fact that the red light is least scattered even through the thickest atmosphere of the even through the thickest layers of the atmosphere. So whenever there is a danger signal, then it will be always shown with red, because red light is least scattered. Scattering of red light takes place very less. Therefore, danger signals are always red. So these are all the very interesting phenomena that take place in our atmosphere. So just for conclusion, the color of scattered light depends on size of the particles. size of the particles, you can call them as scatterers. Size of the scatterers. If the size of particles is very fine, very shorter than wavelength of light, shorter than wavelength of light, then shorter wavelengths, that is blue, shorter wavelength light is scattered. On the other hand, if the size of particles is larger, that is, this is what happens during sunset or just during the sunrise. Sun rays are passing through thickest layer of atmosphere, where large number of particles are coming in contact. So when the number of particles are more and size of the particles is larger, then longer wavelength. Of light are scattered. Then what happens if the size is much larger? If the size is much larger than the wavelength of light, like the drops of water, like water drops, which happens in the, which takes place in the clouds. If the size of the particles is much larger than these air molecules, then colors are equally, light is equally scattered. So it appears white. This is how we can conclude today. So tomorrow we will discuss about little bit more about Tindal effect and we will conclude. Thank you. Have a nice day.